In section 2.1, we saw the first order differential equation graphically with the slope fields, and now we're going to start solving for them symbolically. And the first thing we're going to do is be able to look at a first order differential equation and identify it as a separable differential equation. And if it's a separable differential equation, then we should be able to solve for it with the technique that we're going to discuss now. So we'll do this, and then we'll jump to 2.2, and then I'm going to have you guys try it. I was thinking about having you guys try it as right after we do this, but I think I want you guys to work in groups to try this on your own after I talk about the two different methods. And so you got two methods to try to distinguish. Later on, it's going to be important for you to look at a first order differential equation and decide what kind of differential equation is this. Is this a separable differential equation, or is this going to be one of the other types of differential equations? And knowing what type it is will allow you to use a specific technique. Kind of integration. When you look at an integral, say, oh, that integral is going to be solved by u substitution. You'll look at an integral. You look at a differential equation and say, oh, this is a separable differential equation. I know how to solve for it. All right, a separable differential equation is a differential equation that you can separate, right? That's a convenient name for it. Should actually enjoy that because some of the names aren't going to be so convenient later on. The idea of being able to separate this is that you're going to have your independent variable and your dependent variable, and those are the two variables that you're going to try to separate. Now, if you have something that you're multiplying and dividing, those things are pretty easy to separate. When you start introducing addition and subtraction, that might make things a little bit more complicated, and you might not be able to separate it. So not all of the first order differential equations are separable. So you have to know when to separate and know when you cannot separate and use something else. I also want to introduce another possible notation that might come up. Well, before we do the notation, since we are already here about separable differential equations, the idea behind separating a differential equation is to take a look at it and say, oh, there's a dy dx, and then there's functions with an x and functions with a y. Can I separate those x's and y's? And so if I divide out by f of y, for example, and if I multiply by dx, so we'll have 1 over f of y dy on one side, and on the other side we have g of x dx. Then we've successfully separated this. And now you're looking at differentials. Remember differentials in Calc 1? A lot of instructors just really kind of gloss over the idea of differentials. But when you do a u substitution in Calc 2, you're technically using differentials. You're finding a du and replacing it something with a dx. So those are differentials. So these are differentials. You have a differential with respect to y on one side, a differential with respect to x on the other side. And so the only thing that's left to do is to integrate. And if you integrate this on both sides, on either side, then you have, you can separate these. You've separated them. You can integrate it. You can get rid of the differentials. And then now you just have a relationship between x and y. And then if you can solve for y, then you can explicitly solve for y. And if not, then you might just have to keep it as an implicit solution. So remember the difference between implicit and explicit? We always want to try to get an explicit solution. We always want to try to solve for y by itself. But some cases, when we try to solve for y, you might lose a portion of the solution. And if that happens, then you're not going to be able, depending on your initial condition, you won't be able to solve for what you need to solve for. So usually, if there's anything that you would lose in the process for solving for y, then you just want to keep it as an implicit solution. All right, here is our first example. This is easy. I was going to say this is an easy example. It doesn't look so easy anymore that I look at it. All right, well, Is it separable? This question. Well, it's here, so it must be. So let's see if we can separate it. Um, P of t is a function. It's not p times t. So this is like p by itself. So let me rewrite this just so we don't have any confusions. dp dt is equal to 0.15 p plus 20. So that's my differential equation. I see that there's an initial condition there as well. So we'll deal with the initial conditions later. And so now I want to see if I can separate it. So this is where the addition and subtraction kind of gives you issues. You can't just add the 0.15 p on the other side and leave the 20 there by itself, because then there's going to be issues with multiplying and dividing. So the whole expression 0.15 p plus 20 should go on the left hand side. That's the dependent variable with the p. So, and then I'll take this t and move it to the right hand side. So then I would have dp divided by 0.15 p plus 20 is equal to, well, I took everything over to the other side, so I just have dt left, right? I think from here I can integrate. And if I integrate that, is this the left hand side? Is it, do we want to do partial fractions? Do we want to do integration by parts? How would you solve the left hand side? It's just a u substitution. So if you're not familiar with trying to do things quickly, you know, show some steps. U is equal to 0.15 p plus 20. I would let u equal the whole thing, and then here we'll introduce more differentials. So I would have, to replace dp, I would need to multiply or divide out by a 0.15. So I will have the integral of 1 over 0.15, and then du over u. Okay, so we integrate, and that's just going to be the ln function. So 0.15 ln of u, which is p, or 0.15 p plus 20, is equal to, now there's a plus c that happens here, and you'll see that there's going, whenever you do indefinite integrals, you always have to account for the plus c's, and those things will end up being our parameter for the parameters of curves that we're in solutions. But we will be able to combine c's on the left side with c's on the right side. So we're not going to do the plus c here. We'll just do the plus c on the right hand side, and then it'll be kind of combined together. So t, what's the, well, I already said it, t. And then here's your arbitrary constant. Okay. Now this is one of those cases where it should be manageable to solve for p, so that we can have it as an explicit solution. Eddie? No, we don't do plus c on the left side. You can pretend you're doing it on the left side, and then that would be a different c, and then just pretend that you're adding it over to the other side, and then it'll be just another constant. So the fact that you get a constant on one side, a constant on the other side, and then you can combine those constants, it'll be another constant. We'll just call that c. So otherwise, we would have plus c1 on one side, plus c2 on the other side, and then we combine it to just say plus c. It's all the same. All right, so let's solve for p. We can multiply by 15, so this is going to be ln 0.15 p plus 20 is equal to 0.15 t plus c. And then we'll take the e of both sides. 0.15 p plus 20 is equal to e to the 0.15 t plus c. And then we'll continue on and do whatever else we need to do. So p is equal to, see, we subtract 20 and then we'll divide by 1 over 0.15. And then we have e to the 0.15 t plus c minus 20. Yeah. Oh, because I wanted to multiply this out on the other side. Yeah. You can keep it as C, or technically, if you're going to merge constants together, you would change the C to a C sub 1 or a D or another letter. Usually using subscripts might help. You guys understand his question? Ramsey was asking about distributing this 0.15 to the C, and then that's just another constant. It's constant times 0.15, which is another constant, right? In fact, we're going to do not just that. So we can think about C2 at this point as 0.15 times C. Yes? You could write as C at the end, but like I said, we're going to keep going because this is also the same thing as e to the 0.15 t times e to the C2. C2 is constant. E to the C2 is also constant. And so a lot of times, people just call this another constant. Sometimes they call it A, sometimes they call it P sub 0. We'll call it A. So after playing around with those constants, this is what you'll end up. You got 1 over 0.15 times A e to the 0.15 t minus 20. In fact, you can even distribute the 0.15, and then you would have A times 0.15, which is another constant. Let's do that. But you have to tell me what 20 divided by 0.15 is. What's 20 divided by 0.15? $133 point. Or maybe we just write it as, I thought it was going to be a nicer number. Okay. All right. Unfortunately, this is an initial value problem, which means we have to solve for it. See how that became A naught? A naught is actually like 0.15, 1 divided by 0.15 times A. So that constant kind of morphed along the way, right? All right, let's plug in the value for our initial condition. That says P of 0 is equal to 100. And then we'll put that into here. Why are we putting that into there anyways? What are we trying to solve for? The what? The constant, the arbitrary constant, which has now become A naught. So we're trying to solve for A naught. So P of 0 is equal to 100. I'm just rewriting everything over again. So we have A naught e to the 0.15 times, and then this is where you put 0, and then minus 20 over 0.15. So we're going to put that 0 in for t. And then now we have an equation that only has an A naught, and then so we should be able to solve for this. So this is 100 is equal to A naught times 1 minus 20 over 0.15. Let's subtract that over 100 minus plus 20.0.15 is equal to A naught. So whatever that is. Can somebody find a nice number for me without the 0.3333? A fraction? Can you make that into a fraction? The whole thing? 700? Probably could have written the other side a little bit easier, nicer too, but this is it. This is your particular solution. So let's label these things. This answer that we got here was our general solution. And the general solutions tend to have your arbitrary constant that we haven't solved for yet. And here, after we have solved for your arbitrary constant, we get your particular solution. And then there we have it. Okay. All right. So that's a general idea behind what are these things called again? Separable differential equations. So that's a general idea behind separable differential equations. If you can look at an equation, you can separate it, then that's great. Okay. We're going to move on to see if I can introduce the next topic for from the next section, and I'm going to have you guys practice working on separable differential equations on your own, as well as this new technique. So the next technique that we're going to do is looking at a first order linear differential equation. So this requires a little bit more legwork to try to understand. But it also kind of hinges on the idea that, well, you know what a linear equation should look like, right? So if you know what a linear equation should look like, then you know what a first order linear equation should look like. Didn't I do my paper size? So a first order linear equation can be written this way. Remember, a linear equation has all the functions and its derivatives. The functions and its derivatives are not raised to a power or not taken. It's not composed with anything else. But you might have functions of x's, functions of the independent variable being multiplied and that's still okay. It's still linear. And so the standard form, or one of the forms that we can be looking at, would be a form where the dx dy is not solved for by itself, but we can write dx dy by itself as a with a coefficient of 1, and then we have a y is the other part of the function. The idea is that if you can see your first order linear differential equation written this way, then you have y, dy dx, and y being added together with some other functions. And then for now, ignore the other side, f of x. And so what we want to do is, if you remember the, what's this called? Product rule. If you remember the product rule, d dx of fg is equal to, what is it, derivative of the first times the second plus the first times the derivative of the second, or some combination like that. So if you can imagine that this, one of those terms might be your y, then the idea is that, can we multiply something so that, can we multiply your differential equation by something so that it kind of mimics the product rule? And it turns out that you can. And the idea behind this is, if we look at this thing as if it was a product rule, it might not look like a product rule right now, but if we multiply this by some function, can we make it look like it was a product rule? And so if we do that, the product rule would end up looking like that function mu, this is the Greek letter mu, times y. So we're going to want the left-hand side of your differential equation to look like this: mu times dy dx plus mu times p of x times y. So for this to make sense, this is kind of like the legwork to show what we need to get. And then for this to make sense, we have to find a specific value for mu, or specific function for mu. Yeah? Yeah, mu is a function. So it may be a constant, but a lot of times it's going to end up being a function. And so what is mu? We can go through this argument, but the mu is going to end up looking like this. It's going to be the exponential function raised to the integral of p of x dx. Okay? So so this argument is in the textbook. You can look at it. Could probably share a video of somebody explaining this process as well. But what I want to get is basically the algorithm out of this. So if we can get an algorithm out of this, then maybe we can work with it. So here's what we're going to do. Let's just do an example. All right. Let's do an example, and then we'll see how you can kind of mimic the example. I have 3 times dy dx plus 12y is equal to 4. So this is our example, and the first thing you look at is you ask yourself, is this a separable differential equation? Because if it's separable, then that's a lot easier to deal with. And you have to convince yourself that, no, this is not a separable differential equation. There's no way you could try to work this out to be able to, actually you can. Let's throw an X here. Now it's not separable. All right, so this is not a separable differential equation. Because if it was separable, then we could solve for it using separable. But this is a first order differential equation. You got the dy dx, you have the y, and then you have other constants and other functions of x. So this is a first order linear. And now that you know that, we can apply this process. So this is the algorithm. What you're going to do is identify the p of x function. The p of x function is the function that's next to the y after you've written the coefficient of dy dx to be equal to 1. So what's the first step? What? What's the first step? Say it again? Yeah, divide by 3. So this would be dy dx plus 12 over 3 is 4. So we get dy dx coefficient 1. So now it has coefficient of 1. Now what we want to do is we want to identify p of x. And at this point, now that the coefficient of dy dx is 1, the p of x is the function that's being multiplied with a y. And what is that function? In this case, it's just a constant, but sometimes it could actually be a function. Okay? So the next step after that is to find out your integrating factor, it's called. So our integrating factor is going to be mu is equal to e raised to the power of the integral of p of x dx. Okay? Yeah. E to the integral of p of x dx. Yeah, it's always going to be like that. And so this is, what is the integral of 4x? Now, indefinite integrals, right? Plus c. So we can do this process with a plus c, but you'll see that eventually that plus c will merge into the plus c later on. And so you'd have to actually go through the work to find that. And I'd go through the work for you, but it's more fun if you do it yourself. So this is our integrating factor. And the integrating factor is going to be what you're going to multiply the differential equation by so that you can, so that the right-hand side would become a product rule. So we're going to go here, and our next step is multiply the dE by the integrating factor. So our differential equation was dy dx plus 4y is equal to 4/3 y, so we'll multiply everything by that. So e to the 4y times dy dx plus 4e to the 4y, oops, that's 4x, sorry, times y is equal to 4/3 e to the 4x times x. Okay? Is that part clear? What, you can't read my writing? All right, so e to the 4x times dy dx plus 4 e to the 4x times y plus 4/3 times e to the 4x times x. Okay, so this part here, it's not a coincidence. We actually, the whole reason for doing the integrating factor is to make sure that the left-hand side is written as a, the left-hand side is written as a product rule. Yeah, that's what I meant to say. So if you look at the left-hand side carefully, we have the first times the derivative of the second plus the derivative of the first times the second. Doesn't that look like a product rule? Note the left-hand side, LHS, left-hand side is a product rule, which means we can rewrite this, the left-hand side, as d dx of what are the two terms? E to the 4x and y, right? If we take a look at e to the 4x and y as f times g, then what we have here is f times g prime plus f prime times g, product rule. And if you did the integrating factor correctly, you're guaranteed that this is going to happen. Okay? So that's the left-hand side. The right-hand side is still the right-hand side. We haven't done anything. Now what we're going to do is, well, we have a derivative of a product on the left-hand side, and we have some expression on the right-hand side. And I want to solve for y. Y is on the left-hand side, right? How do you undo a derivative? Integrate. We're going to integrate. And fundamental theorem of calculus says the integral of a derivative is going to be the original function. That's going to be left-hand side is the original function, plus c, but the c can go on the other side. So when we integrate both sides, the left-hand side would undo the derivative, and so that would just leave you with e to the 4x times y. And then the right-hand side would, how would you solve for this integral? Integration by parts. Yeah? Oh, yeah. We'll throw a dx in there. Sure. Oh, we'll do it in red. Not that you can see red on the screen. Can you see red on the screen? Okay, so we undo the derivative on the left-hand side and the right-hand side. We have to do some work. Integration by parts, I think you let u equal to x, and then you let dv equal to 4x or something like that, and then yada yada blah blah blah. So I think this is going to be 1/4 x e to the 4x minus 1/16 e to the 4x. Okay. So y is sitting over there almost ready to be solved for. Right now it's an implicit solution, but we can just, divide out by e to the 4x, right? So let's do that. Y is equal to, we could probably do some more manipulating here. Let's distribute the 4/3. So that'll be 1/3 x, e to the 4x and e to the 4x would cancel. And here the 4 would cancel, but then you'll still get a 1/4 and 1/3. And then the e to the x would cancel, e to the 4x would cancel. This one will not cancel out an e to the 4x. So, say it again. I think it's 1/4 after you cancel, but then you're still multiplying by 3 in the denominator, right? Yeah. Okay. So this is your solution. What kind of a solution is this? It's a general solution because there's a C. We haven't solved for that. We don't have an initial condition, so we can't solve for that, and so we're done. Okay. Any questions? All right. So what I'm going to do is I wanted more time for you guys to work on a couple of problems. So instead, I'm going to just have you guys work on section 2.2, which is the separable differential equations, and then I'll try to find a way to have you guys practice this differential equation. So we're going to get into groups. Have we gotten into groups in this class yet? Four, 6, 8. So groups. Maybe pairs. Ah, just two people. Are you guys both here? Yep. Do you know each other? Cassie and Tuya? Okay. You guys are one group? Ping? Wing? Raise your hand higher. Ramsey and Bing? Behind you? Oh, now we got, Eric too. There's Eric here? Okay. So you're with Ramsey and Bing and Haying and Jose and Rupesh? You guys got everybody? You know who? Is Rupesh here? Rupesh, are you here? Nope. Let's move you out. Thomas, Eddie, and Daniel? Okay, you guys got each other? Jenna, Ivan, and Lesong. Bernardo, Justin's not here. Bernardo and Malcolm. And Hong Hao, Yao, and is everybody here? Okay. All right. So get yourselves together into groups. I'm going to put the problems on the screen. So there's 4 problems. So group one will do problem number 1. Group 2 will do problem number 2. And then group 5 will do problem number 1. Group 6 will do problem number 2. You know, the mod remainder. Where are the problems? Oh, there it goes. Here are the problems that you guys are going to work on. So we're doing inseparable differential equations. Get together with your groups, do one of these problems, and then I think we'll have time to do 2 of the problems. So just make sure you're able to do 1. And then you guys can start the next problem down if you finish. Yeah. Michael, do you know? Jose, just you 2. Yeah. Oh, so we have 5 minutes left. So what I want to do is I want to let you know that this is an assignment that would go under a worksheet. We'll call it worksheet number 2. But actually, I wanted 2 problems for you guys to do. So we'll continue this process. But the idea is that I'm going to want you and your group, to videotape one of you or both of you explaining this, either on the whiteboard or on a piece of paper. You don't have to show your face if you don't want to, but that's totally optional. But I want you to videotape you explaining the process of how to do the problem that you're working on. Okay? And that's going to be submitted as part 1. And then next time we'll come back and talk a little bit more about what was that? First order linear differential equation. I'll do one more example, but I'm going to have you work out your second problem. I'll post this up. You have a second set of problems, and so you and your group will focus on one of these, the same numbering system. So groups 5 through 8, whatever number you land on. Group 1 will do number 5. Group 2 will do number 6, etc. Okay. So this is your second problem that you're going to do. So you're going to submit 2 videos in the assignment, and you only need 1 submission per group. So if there's 2 of you, there's only 1 person needs to submit, and then the other person is going to get credit for that because you guys are attached as a group. Okay. This will be due probably on Wednesday next week. So, I'm just running all the time.